Okay, welcome everyone. Thank you for joining this special session on one of the forecasting tools we have developed at the international desks. This tool is a tool to detect environments for hail and severe weather, and it works pretty well. So we're gonna go a little bit more into detail on the tool by showing a couple of examples and also showing all the details behind the construction of the tool. So let's get started with the presentation. So the tool that we developed is called GR02T. I'll explain the name in a little bit. We actually want to improve this name and change it, but this is the name that we have been using since 2019. And this is a tool that has the goal of improving the detection of environments favorable for hail and severe convection. So the motivation for the development of this tool was that hail poses a very important threat across the mid-latitudes of South America, particularly within the Paraná and the Río de la Plata basins. I'm going to jump and show you where I'm talking about. I'm talking about this region in South America, the Paraná and Río de la Plata. So this is kind of equivalent to the eastern side of the Rockies and the plains of the United States in terms of geography. We have a very tall mountain range. Oops, look here. Okay, we have a very tall mountain range, which is the Andes, and we're in the mid latitudes and subtropical parts of the continents. So this is where very warm air masses that come from the tropics interact with upper tropospheric systems that are in the mid latitudes, right? So something similar happens in the US. A little bit further north compared to South America, but you have these like tropical air masses that come from the Gulf of Mexico, but then there's these cold troughs that comes from the west, and Erin can verify this. There's a lot of hail in Colorado and areas just east of the Rockies. And South America is kind of similar, even though the geography is a little bit different. The impacts are kind of the same. So I'm going to go back to the previous slide. Uh, so as you can imagine, in South America, the amount of observations available, it's way less than in the United States. So in the United States and in Canada, there's more surface stations, there's more people, the population density, people with cell phones, and so you get a lot of reports. And also you got a great observing network, and a lot of people working on the field. But in South America, not only the community working on the field is very small, but South America is more sparsely populated. So it's very hard to really verify where the hail is occurring, and also forecasting the hail. There's less data. If you look at the map in South America, if you look at the U.S., in the U.S. It's pretty wide, right? East-west is pretty wide, and you got a lot of data coming in, and also data from the North Pacific. Whereas in South America, the data coming into the models comes from the west, comes from the Southeast Pacific, and this region of the world has very few observations. Most of it depends on satellite. Again, that is why satellite is important. So models are not that great at forecasting hail in South America, and also verifying is a challenge. So due to these challenges, there's always been a need to have tools that help them to forecast hail, because the hail can be very impactful. It generates a lot of trouble. So this is the reason why we developed this algorithm, the GR02T, to help with the forecasting of hail in the region. Where does hail occur in the Americas? Hail actually occurs in a lot of regions. There's a small hail actually in the Andes and in the elevated terrain in Mexico and in Central America. And the reason why you can see small hail occasionally in these regions is, even though we're in the tropics, is because the terrain is really high up. Therefore, most of the clouds that form, the diurnal cumulus that form, are already, or they develop glaciation very quickly. Therefore, the hail formation layer is very close to the surface, and it's very easy for the hail to reach the ground, to form and reach the ground. Of course, you need strong thunderstorms for this, right? If you have just a cumulus cloud, it won't necessarily form hail. But if you have a strong thunderstorm with a strong updraft, this will be very easy for it to generate small hail. And actually, small hail can be a problem, especially in big populated areas like Mexico City, which is here, in Bogota, Colombia, which is here, in Quito, Ecuador, and La Paz, Bolivia, for example. There have been occasions where hail has been a problem because they don't necessarily get very large hail, but they can get a lot of small hail in these regions. And the small hail can block the drainages and make heavy rainfall accumulate and enhance flooding. And so hail can be a significant issue in these locations. And more than that, it can also affect crops. So this is something that happens all over the Americas. However, the algorithm we developed is not designed to forecast this type of hail. This is something I would like to do in the future, develop an algorithm for that type of hail, the hail that happens in the elevated terrain in tropical regions. Actually, this algorithm is designed to simulate a second type of hail, and this is the hail associated with severe thunderstorms. So whatever is yellow in the map. And this is what we were talking before. These are the areas that get a lot of hail from severe convection. For example, the plains of the US are a region that gets a lot of hail from severe convection, especially just east of the mountain range. And also, South America gets a lot of severe convection just east of the Andes. But this area extends into Paraguay here, into southern Brazil, and into Uruguay. So it's not only Argentina, but it's this whole region. So the algorithm GR02T is designed to help forecasting this type of hail. There's a third type of hail that in reality is not really hail, but it's graupel and sleet. In some parts of the world, graupel and sleet can be confused with hail, but the formation process is a little bit different. So it can be seen as soft hail, but it's not really hail. So parts of South America that get really colder masses coming from the south and the southwest, occasionally they can get this very small hail, as well as Patagonia. But this is actually graupel or sleet. It's not necessarily hail. So this is a little bit different. Okay, so where does hail occur in South America? As we were showing before, there's a lot of there's lack of data in South America, and to really know exactly where hail occurs and where it doesn't, there's a study that is the most comprehensive made in Argentina, using data from about 48 years. And there's also another study made in Germany, but this one uses satellite data. Again, satellite data is very important because it covers areas where you can find observations. So this one uses satellite data, but also uses ERA 5 data to use the environments favorable for hail. And then you join. They looked at the overshooting tops using satellite data and filter them, looking at these environments favorable for hail, and made this hail climatology. So there's very little of information about the hail climatology, as you can see, but we have some ideas of where hail can occur. So if you see the climatology of Argentina, this was done in 2012, you can see that the regions that we described before are there. So the high altitude hail or elevated terrain is there. So this northwest corner of Argentina, you get that. Then in the Patagonia, this is actually graupel. It is classified as hail, but in reality, this is graupel or sleet, right? So this comes from a colder cumulus. And then the hail associated with severe convection, with severe thunderstorms, is this one here that you can see from northeast Argentina all the way into the Andes. The Andes are in the western end of Argentina. This is consistent with this climatology constructed with satellite data and ERA 5 model data, reanalysis data. The one region where there are discrepancies is here in the triple border between Uruguay, Brazil, and Argentina. Apparently, there are not a lot of observations in these stations of hail. I don't know the reason. As you know, observations from observers could also have problems, right? The observers, I mean, we try to make everything standard so we can observe the same things, but it doesn't mean that people are occasionally going to observe something different. And also, the data itself from satellite and from reanalysis also has problems, right? Because satellite cannot see everything, and the reanalysis are also an approximation. So This is the only region where we have discrepancies, but in general, you can see that all this corridor in mid-latitudes of South America is a region favorable for hail. So the algorithm was tuned for this region, basically, for this part of Southeast South America, around 30 degrees of latitude, right? So this means that in the North Hemisphere, if the algorithm works for severe convection between, say, 25 south and 40 degrees south, it should generally work in the Northern Hemisphere for similar latitudes, right? Because North Hemisphere and South Hemisphere are kind of mirrors. They're not exactly the same, but they're analogous. All right. I'm going to jump. I need to compile more information about the impacts of hail in South America, but as you can see, there's not a lot. So this is kind of a challenge, but this is something to build on. So let's go into the tool. So this is the tool that we developed, the GR02T. And the first time when we developed this tool was in 2015. We developed it, I developed it with Néstor Santayana. So Néstor Santayana is a forecaster from the Uruguay Weather Service. Well, was a forecaster. Now he's higher up in the Uruguay Weather Service. And he came to train with us at the international desks in 2012 and brought this, concern about the need of becoming more skillful in forecasting hail. So we started merging his information, whatever he had worked on, all the information he had taken, all the data he had noted whenever there were hail events in Uruguay, and we used the software WinGrids, and then we developed this algorithm. So the first version of the algorithm was GR01 or Granizo version 1. GR stands for Granizo or hail in Spanish, so Granizo version 1. And this was released in 2015. This version was very, very simple. It only looked at 3 parameters, but it was useful. I mean, we could see that it helped us to forecast hail. However, with time, we made a more complex algorithm, and we released it experimentally in 2019. And this is the one that I'm talking about, the one that I'm discussing here, the GR02T. Okay, so this is the GR02T hail algorithm, and I'm going to explore the algorithm using the severe weather event that happened last Saturday in Southeast Paraguay, Saturday night to Sunday. As you can see, I'm just putting a video showing the hail. You can see hail of different sizes. You have large hail and small hail. So they got all sorts of hail, and it's happened in this part of Southeast Paraguay during Saturday and Sunday. So this is the output of the algorithm. There's a lot of things on the output, but I'm gonna, hopefully you can understand everything that is plotted in the graphic by the end of this presentation. All right. So how to interpret this algorithm, the GR02T? So the risk for hail is indicated with boxes over shaded areas. So we use green boxes, and the color, as the risk increases, we use red boxes, and then we can call them pink or magenta boxes when the risk is higher. So if we just look at the boxes, we already have an idea that we might have a chance for hail. So for example, here in the figure, we can see there are some green boxes. So in this region, there could be some chance for hail. But whenever we start seeing that the boxes appear over these colored areas, so in this case, we can see a green coloration. This enhances your confidence in that hail might occur. Why? Because these shaded areas are designed to describe the risk for severity. So they don't look specifically at the risk for hail, but they look at other parameters associated with severe weather. And whenever you have more factors favorable for severe weather present, you start seeing more colors, also going from green to red and to pink. So whenever you see these boxes located over these shaded areas, the chance that you're going to get hail increases. So your confidence in forecasting hail increases. All right. So in this case, we can see the satellite animation for this event. We can see the cloud signatures in this image are impressive. If you can see the convections, they form these like U shapes with a little dot in the middle. This is called the overshooting top. You can see some of these storms developing the overshooting tops. And these V signatures are a chance of severe convection. So basically, these little black dots that form, these are the updrafts that penetrate, in this case, they penetrate the tropopause and reach really high altitudes. And then they form this V-shaped signature in the cirrus cloud. So these are very, very strong storms. And as you can see, I encircled the area where we had the strong storms with black. And this was consistent with the algorithm in general terms. So you can see here the black area. And at the beginning of the period, around 03 UTC, we got these boxes over the green shaded area. Uh, and this is where these storms developed. And then later on at the end of the cycle, we got the color shades and even a red. So here the chances for hail increase, right? The chances for severity increase. Now you have a red, meaning that you have a higher chance for severe convection, and also you have the boxes over this area. A final thing I wanted to let you know is that we added a contour as well. You can see these red contours, and in occasions you'll see a red contour and sometimes a pink contour. So these contours are also based in parameters that we use to detect the chance for hail. And whenever we see a red contour around the boxes, that means that the parameters are particularly enhanced, meaning that your chance for hail is even higher. So whenever we see these red contours around the boxes overlaid over a shaded area, the chances for hail increase. So what are these shaded areas? I'm going to explain later in the presentation because there's a lot of information, but I'm going to explain later in the presentation what these shaded areas are, how they are calculated. But basically, these are areas that describe, they provide a general description of the risk for severity, where convection is present, right? So here, this is the background of the screen, the normal background of the screen, dark, very dark gray. Whenever we see this very dark gray, the algorithm is saying, oh, in these regions, there's no chance for strong deep convection. It's not expected, so you shouldn't worry about anything. So these are regions where you might have fair weather, or if you're going to have any precipitation, very likely it's going to be warm convection or something mild, nothing severe. Now, whenever you start getting the grays, for example, in this area here, the algorithm is saying, in these areas, you might get strong deep convection. But since we have gray, we do not see a potential for severity. It's just a couple of strong thunderstorms if they form here. Now, when you start seeing greens, then there's a chance that some of the convection could become marginally severe. A couple of the cells could become severe. And once you see the red and the pinks, that means that there's a higher chance for those cells to become severe. This means that there are many factors that favor severe weather in these locations that are present. So these categories just provide a qualitative idea of whether you might have severe convection or not, but they don't speak about specific risk. I mean, if I see these colors, I wouldn't be able to say, oh, we're going to get hail, or oh, we're going to get tornadoes, or oh, we're going to get strong winds. I can only speak about the general description of severity. So these color shades are kind of background information to help the forecaster gain confidence about a general chance for severity. Now, if you want to define whether you're going to have a chance for, say, water spouts, tornadoes, strong winds, then you need to make your own analysis in these locations. All right? So this is just to help the forecaster. It doesn't really provide specific information about severity. Now, so in a nutshell, from all I spoke in the last couple of minutes, overlaying these areas with the boxes over these areas with a general risk for severity enhances the confidence. So in this case, we can see in these two areas at the beginning of the forecast cycle and then around 6 UTC, the algorithm is saying, okay, you got a risk for hail. and you got a moderate risk for hail. We had these like red contour and red boxes, and overlaid over a region with a marginal risk for severity. So I would expect severe convection here, marginal to slight risk of severe convection with some hail. And this is what happened. You can see the severe cells forming in this region. And at the end of the cycle, there is some another another region forms of the chance of severe convection here, just west of this southern part of Paraguay. You can actually see these cells popping at the end of the loop. Yeah, but the convection that is located here entering Brazil, so this area is already Brazil, right here. According to the algorithm, these have a higher chance for severity. Now, in this case, we would need reports. Wasn't able to get reports from Brazil, but I was able to get reports from Paraguay. And as you saw, they got a lot of hail of different sizes during this event. Let's speak about what are the other fields included in GR02T, because right now we spoke about the chances for hail and severity, which are basically these boxes and contours over the shaded areas. But if you look at the algorithm is really complex. There's a lot of other stuff plotted, and it's a lot of information. As you probably know, if you've seen the things that I've developed before, sometimes they're a little bit crowded. That's good and bad. Bad because there can be confusing. There's a lot of stuff going on, but good. They can be good as well because we're looking at different things that are useful to generate a good forecast. So in this case, we have plotted a lot of other things in the output of the algorithm that helps us analyze the synoptic situation. So let's start one by one. So we have the low-level winds. The low-level winds are plotted in color green. In the last version of the algorithm, I added this light blue just to show the stronger winds. These are winds that are in the 925, 850 hectopascal layer. And why choosing this layer? Because this is a layer that usually associates with the presence of the low-level jets. And the low-level jets can have a very, very strong impact in the formation of severe convection, as folks in the Caribbean might know, right? Low-level jets are very important. In the case of South America in this image, and apologies for those in the North Hemisphere, I know most English speakers are in the North Hemisphere, but this is for South America. So in this case, we have a low-level jet from the north in regions where you might expect enhanced convection are in the exit of the low-level jet, whenever you get this strong moisture convergence, and also on the cyclonic side of the low-level jet. So in this figure, I would expect the most severe convection just looking at the low-level jet, nothing else, in this location right here. This is what I would expect because we got the converging exit of the low-level jet and cyclonic rotation in this region. Yes. So this is something that we plot. We plot the low-level winds for the low-level jets. Then we also plot the upper winds for the upper jets. So as you can see in the image, we're plotting above a certain threshold. So in this case, in this particular case, we can see these very strong winds. This is about 140 knots. Yeah, 140 knots from the southwest. This is an upper jet that is basically breaking in this region. If I know it's hard to see, but if you look at the wind barbs, we got an upper jet that is breaking in this region. So the cold exit of this jet is located around here. So if you know upper jet dynamics, whenever you have an upper jet, let's do the south hemisphere here, south hemisphere, and then the north hemisphere right here. So if you have upper jets, the areas where you're going to have enhanced upper divergence and rising motion are going to be the cold exit in the south hemisphere would be here. This would be divergence. In the north hemisphere would be here. We will get enhanced divergence. And then the warm entrance. So here you will get enhanced divergence. So this is called the cross divergent divergent pattern around jet streaks. So in the south hemisphere, once you get this jet from the southwest, the cold exit would be in this location, right? Would be approximately here, which coincides with the region where the algorithm is suggesting the presence of hail. So this is already giving me confidence. See, just by analyzing the low level flow and analyzing also the upper flow together, I'm gaining confidence that the synoptic pattern aligns with what the algorithm is telling me. The algorithm is saying that, oh, you might get hail in southern Paraguay, but if I understand how the low level winds and the upper winds interact, then I gain more confidence that these could actually materialize, right? Then something else that we're plotting for reference is the upper divergence. Remember that model, this is all the model, right? This is all GFS. And sometimes if the model resolves convection, it can generate its own upper divergence. That's why it's so important to understand the synoptic pattern, right? In this case, we spoke that before that we have this upper jet and the exit region of the upper jet should be upper divergent, this region here. So in this case, I am believing the model when it plots these yellow contours because I expect upper divergence in this region. So this is something else that we're plotting. Wherever you have enhanced upper divergence, that will favor your ascent in the column. So now we have another thing that is helping us to conclude that that region where the algorithm is forecasting hail could be correct. All right. The next thing that we're plotting are the temperatures in 500 hectopascals. And why do we plot that? This is a parameter that is used in a lot of algorithms and in a lot of indices. For example, the Lifton index uses it, the GDI uses it, a lot of the total totals, the Showalter, a lot of indices use that. Why? Because 500 temperatures relate to a lot of things. First, they are located usually in the top of the region where convection, where the updrafts form. You know, once convection starts forming and it breaks the cap of the stable layer closer to the surface, it will start like growing vertically. And 500 hectopascals is a good layer to compare with the temperatures of the surface to understand how strong that updraft is going to be. So it's a very important variable for that. Another thing why 500 is important is because it usually helps you to see where these upper troughs and ridges are. Upper troughs are associated with cold air, and upper ridges are associated with warm air. So in this case, particularly in these subtropical locations, you can see just by plotting 500, you can see where the trough axes are, right? So in this case, we can see that this is the contour of -16. I'm going to highlight it. This is -16, right? So we got an upper trough, a broad upper trough located in the south of the figure. But if you look at these contours here, we got a shortwave trough. You see this cold axis here. We got a shortwave trough that is crossing into Argentina from Chile. Here we got another shortwave trough, just by looking at the contours. And here we have another shortwave trough, right? So these temperatures will help you to see where these shortwave troughs are, and these play an important role in highlighting ascent as well. So this is one of the reasons why we have the 500 temperatures plotted in the algorithm. Another reason is that we want to see what is the value of the temperature in this layer. Why? Because since most meteorologists are familiar with using 500 hectopascals, we're usually familiar with which temperature we need to get severe convection in our regions. So for example, in the Caribbean, in several of the islands, particularly in the Greater Antilles, I know that they use the temperature of -8 at 500 to forecast a potential for severity. So if your mid-level temperatures are below -8, your chances for severity increase. This applies to Hispaniola and Puerto Rico. I'm not sure what they use at Cuba. I'm not sure if it's -8 or -9, but -8 or -9 are usually thresholds that are used to forecast severe convection in terms of instability. So this is another reason why we have these temperatures plotted in the graphic. All right. Any questions so far before I finish this slide? And for Alan, we should have red boxes and contours ranging from green to red. What happens if we have an area with green boxes and a green contour? Yes, we're going to get to that. But basically, if we get an area, I'm going to explain that. But here, for example, when we get an area with green boxes, the chances for hail are really marginal, according to the algorithm, right? In this case, whenever we have a red box, your chances for hails are higher, and if we have a contour, they increase. The contours we're plotting are only red and purple. For green, we just don't plot contours. So here, in this image, if you see here just to the east of Paraguay, we have some green boxes alone with no contour. So what this is saying is that your convection might be strong. The convection is strong. And you might have a chance for very, very, very isolated hail, but there's a lot of other parameters missing. So I wouldn't necessarily forecast hail here. If I would forecast here, I was just looking at this, I would just forecast strong convection. The chances for hail are really, really marginal. Whereas here, when I start seeing the red, and if I start seeing contours, then my confidence in that hail might occur increase. So here I would forecast hail. And here we have a short wave trough, as we discussed before, so that gives me more confidence. We also have the cyclonic exit of the low-level jet, so this might be a region where hail is starting to form. And this region also has even a stronger signature for hail. So here I would forecast hail. All right, so this is another example of the interpretation of the algorithm. Pardon the text in Spanish, but as you can see, there's a lot going on in this figure, and again, it's kind of crowded. But something to highlight in green, I highlighted the low-level jet. So again, you can see that you have a jet from the north. In the northern hemisphere, will be from the south usually, but in this case, it's from the north, from the tropics into the exotropics, and we have the cyclonic exit of the jet. So this gives me confidence in this yellow box being a region where hail might occur. Another thing that I see is a short wave trough that is negatively tilted. Negatively tilted means that the side of the trough towards the tropics, it's ahead of the side of the trough that is toward polar regions, right? So it's tilted this way. So this gives me also confidence that you might have hail here, because negatively tilted troughs usually enhance ascent significantly, especially downstream, and this is propagating this way. Another thing that enhances my chances for hail is that if you look at the barbs here, you have the entrance of an upper jet, anticyclonically curved upper jet. So this is also a region where you might get enhanced ascent. So what I wanted to conclude with all this is that understanding the synoptic pattern is key. So don't just look at the algorithm blindly, but also try to understand what is going on with the synoptic pattern. All right. How does the algorithm compute its fields? The algorithm has three parts. So the first part is basically just deciding if there is a potential for convection, for strong deep convection to form. So it looks at 5 parameters that I'm going to show in a second. And if all the parameters coincide, it says, okay, yes, there's a potential. So if the parameters don't show that potential, then nothing happens. But if the answer is yes, then what the algorithm does is first, it evaluates the severity potential, how strong the severity potential is, and then it also evaluates the potential for hail. So these are two separate things. So part one, defining if there is a potential for strong deep convection. So these are the 5 parameters that we evaluate. And this was, again, this was tuned for South America. So we try to make it as general as possible, but the algorithm might need to be tuned for different regions because of the climatologies that vary, right? So for example, this algorithm doesn't work that great in Colorado. When I was there in May and June last year, the algorithm wasn't that great because the climatology of Colorado is too cool and too dry for the algorithm. right? So if I want to capture the type of convection that happens in Colorado, probably I would need to change these parameters. For example, lower maybe the precipitable water threshold, maybe change the lifted index threshold, and the mid-level temperatures probably bring them down, and so on, right? So uh, you may it may the algorithm doesn't work exactly the same for every location. It might be tuned depending where you are. Anyway, so to decide if you have a potential for strong deep convection, these 5 parameters need to align. So if one of these parameters doesn't reach the threshold established, then the algorithm says, nope, there's no chance for deep convection. So you need the 5 of them to reach these thresholds, right? So the things that we're looking at are total precipitable water. We're looking at relative humidity, and we're looking at this layer 500 to 700, which is a layer where hail usually forms. Then we're looking at the lifted index. The lifted index or basically assesses instability if you raise a parcel from the surface to 500. Then we're looking as well as ascent resolved by the model. These are the omegas of vertical velocity in pascals. And then we're looking at temperatures in the mid-troposphere. Okay, so if all these parameters pass, and the algorithm says, oh, okay, so there's a potential for strong deep convection at this grid point, now we go to part 2, which is assessing the risk for severity. The risk for severity is assessed using 7 parameters. There's a lot of information on this slide, but you'll have the presentation. So these are the 7 parameters that we look. And what we do is basically start filling that grid point with values depending on how strong how much do these parameters exceed the thresholds. So for example, we look at cold air aloft. We look at temperature of 500. So if the temperature is lower than -8, we start adding value to the risk of severity. But if the temperature is say -20, then the value that we're going to add to that risk of severity is much higher, right? So it depends on how far away we're from that threshold we established. The next parameter is an enhanced deep layer instability. We also look at the lifted again, but this time if the more negative the lifted index becomes, the more we add value to this severity risk. Another parameter that we looked at is the lapse rate between 700 and 500. Another one is the omegas, the ascent in this layer. Notice that the layers that we are using are in this graphic, right? So for the cold air, we're using 500 hectopascals. For the lifted index looks at parcels that raise from the boundary layer all the way to 500. This is these 2 points, 500 and 700. Then we're looking at omegas from 600 to 300. This was tested over South America, and in South America, particularly in the Paraná River Basin, the influence of upper jets is very important. And we found out that when we were using this layer, the algorithm performed better. So this is a layer that we use. Then we're looking also at the convergence of the flux of mixing ratio. This is basically moisture convergence in this layer underneath. And then we're looking at shear. Shear is very important for severe weather. So we're looking at 2 layers of shear, 0 to 3 kilometer and 0 to 6 kilometer. We're just looking at bulk shear, which is just the magnitude of the difference of the winds. That's it. And then finally, we're looking at upper divergence in this layer up here. As you can see, if you're familiar with severe weather parameters, not all of these are necessarily severe weather parameters. If I have upper divergence, I won't necessarily have severe weather. This just enhances the ascent, right? Also, if I have low level convergence, this just enhances the convergence of moisture. Doesn't mean that we're going to have severe convection. But these kind of add up to kind of enhance the risk for severity in the region. From all of these parameters, the ones with a star are the ones that are more closely linked to severe convection. And as you can see, there's a lot of room for improvement in this part of the algorithm. Basically, something that we could do for a future version once we develop it is to increase the weight of these 3 parameters. Also play a little bit more with the shear because the shear is super important for severe convection, and so on. So this is an area where the algorithm could improve. And the last thing before I break for questions is the risk for hail. So for the risk for hail, we just look at 3 parameters. We look at the lifted index again. The lifted index is very important, particularly for South America. We also look at the omegas again and the lapse rates. This 500, 700 hectopascal lapse rate, this seems to be very important in South America because it relates to the strength of the updraft. The larger the temperature difference in this layer, the stronger the updraft. And the stronger the updraft, the larger the hail. So these are the things that we look to establish these different boxes, and we start putting contours as well based on values of these 3 parameters. So the algorithm works pretty well generally. It aligns with official severe weather forecasts in the United States, which is encouraging. There's a lot of folks working with severe weather, very experienced folks in the US. So the fact that the algorithm aligns with their forecasts and the reports, it's encouraging. It works pretty well, particularly for the southern plains. As I said, once you get to the higher plains and the western plains like Colorado and Wyoming, the environment is too cold, so the algorithm may need tuning for that. But once you forecast in convection in Texas, Arkansas, Louisiana, the southern Mississippi, it works pretty well. Then it also works for the Northern Caribbean. This is good news. I know there's some folks from the Caribbean and Northern Central America here. So this is good news for you guys. It does work. Usually you need higher thresholds to forecast hail. And also, I know it works pretty well in the bigger islands. I don't know, for example, if in the Turks and Caicos, the algorithm will work great, just because for hail to form, diurnal heating is many times very important. So the Bahamas and the Turks and Caicos have little land, right? So the diurnal heating impact is limited. Therefore, it's hard for the algorithm to have. It's hard for the atmosphere to have that instability to use whatever the algorithm is showing. However, if you're located in bigger islands like Hispaniola, for example, the algorithm works pretty well. In Cuba, it does work really well sometimes as well, and especially in high terrain, And this is an example of a signal of the algorithm about, this is 2 months ago in August, showing the risk for hail. So the forecasters there know, in the Dominican Republic, they know that if the algorithm shows a signal, then you should evaluate the potential. And they forecasted hail. This is the convection that formed, and there was actually hail. You can see some hail reports, and also you can also see a risk for severity, right? You see the green shades. So there was also some impacts from damaging winds in the Dominican Republic. So it does work for the Northern Caribbean and under certain circumstances. I would say it works even better when you have a strong upper trough present. And if you look at the upper trough dynamics, that will be very important for you to forecast hail in your region. Once you are trying to use this algorithm in the Bahamas, the Turks and Caicos islands that are smaller, whenever you get a signal in the algorithm, this usually translates to squally weather or gusty winds in thunderstorms. Rarely it translates into hail. However, on occasions, in the northern Bahamas especially, that are at higher latitude, I have seen that they have had small hail reports when the algorithm was showing a signal. So it can happen, but it's more likely in the northwest Bahamas than, say, from my understanding, in the southeast Bahamas or in the Turks and Caicos. So since I'm running out of time, so what I'm going to do, I'm just going to jump to the last slides, and then we can look at the current forecast for the algorithm for the Caribbean, and then we can stop right there, if that's okay. So I was mentioning before that there's room for improvement. So this is an event that happened in Argentina, the Villa Carlos Paz event, and they had hail that was 18 centimeters big. It was huge hail. I should have the picture ready here, but I don't have it at the moment. But they had huge hailstones with a lot of damage. The algorithm didn't get it. So if you look at the output of the algorithm, this is GFS 1 degree analysis. You see that there was no signature. The algorithm wasn't able to reach the 5 parameters that reach the threshold for deep convection to be assessed. didn't reach the threshold. At least one of the parameters didn't. So you couldn't have the forecast of hail. I mean, you see nothing there with the crosses. However, I was looking at other parameters, particularly mid-level shear in the mid-troposphere, that relate to hail, and I made another set of parameters and plotted them for the region, and actually you can see that that these parameters did capture the chance for hail. So there is definitely room for improvement in the algorithm, and this is for the next version, right? I'm not going to speak about this with detail because we still need to finish documenting this version, but like with everything, there is room for improvement. Okay. Yes. So Frank, hey Frank, Frank is saying hailstorms are rare events in Belize. However, of the few reported cases, most were observed in the western part of the country, as well as in the northern and southern parts of the country. These storms occurred during the height of the dry season, April to May. No serious damages occurred due to these events. Thank you, Frank. This is great information. This is good to know. I mean, I didn't know Belize also had occasionally some hail. I know Honduras does get some hail in April and May. And the reason, at least I can say that the reason why they get it in Honduras is because at that time of the year, you get the highest temperatures, the highest diurnal temperatures. So the instability that builds up at the end of the day when the storms break in the afternoon inland is very, very large. So the updrafts of those storms can be very violent and violent enough to enhance the generation of hail. So it's good to know that Belize also has a little bit of that as well. So I'm learning something here. Thank you. All right, so we can see the situation in the Caribbean right now, and we have a lot of convection going off. We so let's look at the tools. So I'm going to start with the GDI to kind of have a general grasp of the synoptic situation. Um, okay, so I'm looking at this is the GDID algorithm. So this is not the severe weather. So I'm looking at a trough. We got an elongated trough located across Florida, and then we got in the upper troposphere we got a ridge that is centered just north of Puerto Rico, and we got this diffluent flow in the periphery of the ridge located over Jamaica, Cuba, and the central Bahamas. Then in the low levels, if you look at the flowing gray, we do have, it looks like we might have, I don't know if it's the front, but we do have a boundary that is located, at least we have a surface trough that is located across the central Bahamas, across Cuba, and the GDI is very high in this region, meaning that we have a lot of moisture and instability present in the region. We also have the low-level flow is converging significantly in this part of southeast Cuba and central Bahamas. So there's a lot of moisture convergence in this region and upper divergence. So yeah, the environment is favorable for heavy rain producing convection. This is what I'm seeing. If we look at the satellite imagery, yes, we definitely have a lot of convection going off right now in the southeast tip of Cuba. Some of the convection also in the central Bahamas. So yeah, not too bad. So the GDID is capturing that. Just leave it there. And I'm going to look at the severe weather algorithm. Oh, wow, look at that. And we have the legend in the bottom. So let me put it on the side so we can see it. The analysis of the current situation. Let me go forward in time. This is GFS, right? Look at this. So this is a front. This is a front coming into the Northern Caribbean. It actually hits according to the algorithm, to this GFS run, it's gonna reach the Turks and Caicos and Inagua. This would be, let me look at the date, on Wednesday, October 15, actually on a Spanish session, is going to be crossing this region. And the algorithm is showing something, but in this case, it's only strong convection. I wouldn't forecast hail, but there might be some strong convection moving across the Turks and Caicos and Inagua on Wednesday. Let me keep going forward. Yeah, so this is interesting. The algorithm is actually showing a potential for hail. This is a mild potential for hail for Guadeloupe, actually. This is on Thursday. And this is associated with an upper trough. If you look at the temperature contour here, this is an upper trough. So there are some upper dynamics that could favor some severe convection. Now, I am not familiar with how often they get hail in Guadeloupe. I would think that it's very rare. Not that it doesn't occur, but it's probably small and very rare. So this could mean just strong thunderstorms with strong winds, right? Not necessarily hail. Yeah, it can be used as for forecasting as well, not only nowcasting. So yes. So the idea is that you look at different runs and see how the algorithm evolves from run to run. The signature on Friday morning is also more significant, but this far south, like in the Lesser Antilles, I would just forecast strong convection. I wouldn't forecast hail. Something for them to verify. So this is right now situation. And you can see that the algorithm is only showing a gray, right? It's only the shade that is showing in the region is only gray, which means that strong convection is not showing a risk for severity at least this particular run at this time. And then it's also not showing boxes. It's showing this like red contour here. This suggests that some of the conditions that could favor strong ascent in thunderstorms are present, but there's no chance for hail. There's upper divergence in the region. So there's definitely a chance for strong convection, but not necessarily severe at this time.
There's one last question from Holly. She says, currently you're using GFS data for your tools, which we know its resolution is quite coarse. Do you think the use of finer resolution data like ECMWF or WRF data output can help reduce or eliminate those false hail signals for small islands?
That's a good question, Holly. Not necessarily. And my answer will be not necessarily. I think it's more of a tuning up of the algorithm, because whenever you improve the resolution, you can also increase the noise. Very high resolution models can also actually sometimes they produce stronger vertical motion and can produce more false signatures. So I would think that even though you might get more finer resolution for some events, you might actually have a more false alarm problem. But I'm speculating there. I mean, I've seen it with some higher resolution runs, but in this case, I think it would be interesting to test it with other models, right? I have access to the GFS only at least handy right now, so we're using the GFS, but it would be great to have it with other different models and also play with the resolution.
All right, great. We also have a question from Katia saying, could this algorithm be integrated in seasonal outlooks?
That's a good question. I am not sure, but it's worth the try. The thing is that this algorithm, since it's looking at a specific set of parameters, once you're looking at seasonal outlooks, you might smooth too much these parameters. However, some of the things that it looks could give you an insight of a general increased chance for severe weather. So I think it could be useful. Yes, it could provide some information. Yes, especially if you know the climatology of a location. I think so. Yeah. So something to consider. Yeah. Thank you, Erin. Thank you, everyone.